And all right, so just real quick, it's Thursday, and the only thing due today was you're supposed to tell me who you're writing your famous chemist paper on. You can absolutely change it. Because this class moves so fast, those papers are due in less than 2 weeks. So I'm not sure if people are aware of that. So this would be a lovely weekend to start researching to make sure you're happy with your person. These are the 4 people who I don't have a person for. So if I don't hear from you today, I will be contacting you again. So you can either talk to me in Zoom or send me an email. All right, so Tom and Jerry will erase them. And we're going to talk about titrations today. So again, those of you who had 221 with myself or Dr. Russell or Bernadette, you did a titration, and all of you should have been able to do like 4 titrations this summer, and you would have become so good at it.
Sorry.
Yeah, just mute yourself, Aaron. Thank you. So we're going to go through 3 types of titrations, which is a strong acid, strong base. Whatever comes first, that is what is in the flask. So, or the, the flask. So we have the HCl in the flask. And we're going to be adding from the burette, we're going to be adding the NaOH. So, like on the next page, we're going to do it with a weak acid. So whichever one you're starting with, that number is the same the whole way through. And I'll keep mentioning that. It's what you're adding. So the strong base, this number is going to keep changing. All right, so let me find my blue pen because that definitely shows up the best. So initial is just the HCl, and since this is a strong acid, you can just do negative log of the strong acid, and that equals your pH. Because strongs completely dissociate. That's probably not going to happen on your homework. We're going to be doing it with weak acids and weak bases. But I wanted to always start with a strong plus a strong. And so you get whatever my answer was. So negative log of 0.1, our initial pH is 1. We're going to go ahead and give 2 decimal places to get in that habit. So that was step A. Step B, we have to write an equation because we suddenly are adding a strong. So we have our, in this case, HCl plus NaOH. And the hydrogen, I'm working on grading your test. Blackboard makes this task take much longer. And so I'm about halfway through. I started at the end and I'm slowly working my way up. So if you're at the end of the alphabet, yours has probably been graded. And I hope to have them all done. I will have them all done by tomorrow. Something that a lot of you did the hydrogen, but the hydrogen and the sodium have to switch places, or you have to cross the sodium out. So I'm just going to switch places. So we're going to get NaCl and H2O. Now this is a question a couple people were asking me in my office hours earlier. This is only going to happen in this problem, but the NaCl we can ignore. And the H2O we can ignore. So here's our first bonus point for the day. So who wants a bonus point? Why can we ignore the NaCl?
Is it because, so the sodium is an H or is an A, 1A, and the Cl is a halogen. And so we can ignore those. Because they're together, they're neutral, so we can ignore them.
Yeah, this is a neutral pH. And same with water, we can ignore. So whenever it's on the product side. Now, I want to correct something you said, Harrison. It's not all halogens you can ignore. You can ignore chloride, bromide, and iodide because they are conjugates of the strong acids. If we had sodium fluoride, you cannot ignore that. And we'll see that on the next one. I don't remember what I used. All right, we're gonna do mice charts. That's why Tom and Jerry are here today. Very excited. They were not happy that I ignored them yesterday. The M in the mice chart. So in Harrison, you don't get an answer again. Somebody else can get a bonus. What's the M purpose now? Why are we doing mice instead of ice?
Because we have to find the molarities.
Is that?
I mean the moles.
Yeah, you got it, Margaret. So the M is to find moles. The I has to be in moles. And the reason for that, here we go. So somebody else can try. Why do we have to use moles with buffers and titrations? It's a really tough one. The reason is once we start adding something, you have to use moles because the volume changes. So as the volume is changing, as we're adding the NaOH on this page, we have to do it in moles to find what the change is. And then you can go back to molarity if you want to. But let's see, we have the volume is 0.05 liters times our molarity of 0.1. And that gives us what, 0.005 moles is my HCl. This number, this is going to be the same for every step on this page. So step 2, 3, 4, and 5, the HCl is always this 0.005 moles. Because that was the one that you're adding something to. The NaOH moles is going to change as we go through this, and it wants us to do 20 mils, and it's 0.1 molar. 0.02 liters times the 0.1 molar. I made this simple for me, so I could do the math in my head. These do not have to be the same molarity, but on the next 3 pages, they are, just so I can look really smart in front of you guys and do my math really quick. So this is 0.002 moles. Now this is different from the buffers. There are truly zeros over here. There is nothing on the other side yet in a titration. So titrations are different from buffers. In buffers, you will have something initially to start with on both sides. Now we are ignoring the products in this one because they're neutral, but let's go ahead and keep going. Sorry, I was just seeing what that icon was on my computer. Next step is limiting reactant. So I just write LR for limiting reactant, which means we're going to subtract the smaller one. That's my change. So this is actually makes buffers and titrations easier than what you did at the very beginning when we did the first study set. We don't have plus and minus x's. We know what our change is. It's the 0.002. And that is because it's a one-way reaction. So this is 0.003 moles. This is gone. This side would be 0.002, oops, but we're ignoring it because, again, it's neutral. So this is a strong acid. And you're not going to have one of these. We're going to move to weak acids. But this we would plug straight into, oh, all right. So bonus question time. What's wrong with my math? This is a tough question. You will get the wrong. Go ahead, Jessica.
It needs to be in molarity.
Yes, she's absolutely right. When you plug into the negative log, you have to be moles per liter. This is why I am so particular about volume, about units. The volume is the total of these two. So this needs to be the total volume. So we had 0.05 and 0.02, so that's 0.07. because this is a strong acid, no Ka. No Ka is needed. There was a question on your midterm, I think it was aluminum hydroxide, and it said no Kb is needed. Because if it's a strong, we just plug straight into the negative log, and that will give us our pH. You need to show your units so you know that your moles, and now we're dividing by the total volume to get our volume, and you have the pH. All right. So as we added a strong base, the pH goes up a little bit, but just a little bit. It's barely changed. In fact, I'm not going to go through step 3. When you add 40 mils of NaOH, it goes up a little bit more. So the next step is 1.95. So we're going to sketch a titration curve. So hopefully you have room. You have it around the 40 mils. Maybe I can do a different color. You know what? I wonder if the green shows up today. You guys can tell me. Is the green showing up? I'm seeing.
Yeah.
It is? Maybe enough? Probably not.
Yeah, enough for right now.
All right, we'll see. This is actually, no, we got not enough. We're going to do brown because you have to be able to see it. This is pH, and this is the volume added. So pH is my y-axis, and the volume we're adding is the x-axis. And we're starting really low, pH of 1, and our pH is barely changing. In fact, to 49, we did this once in class, 49.9 milliliters, you haven't even made it to 2 pH. And that is because all you do is you keep making NaCl, and the NaCl doesn't affect the pH, so you still have a strong acid. The strong acid keeps neutralizing the base. You have less and less of the strong acid, but it's still a strong acid, so low pH. And then we get to a special place. And that is our next step, which I'm on step 4. So Tom and Jerry are going to erase most of what I have. All right, the initial moles of the NaCl stays the same. I'm sorry, of the HCl. The initial moles of the HCl stays the same. We're going to change how much NaOH we added. And we're at the equivalence point. Like equilibrium and equanimity, we're talking a lot this term about equalizing. Equivalence means something is equal. And this is the whole point of today's lecture, is the equivalence point. The moles equal the moles. In this case of the reactants. It is no longer a limiting reactant. They are perfectly the same. Again, those of you who had me or Bernadette for 221, you did a titration lab and you remember the colors. I think my class we did 2 different titrations, and it was that moment of perfect color where you stopped. What's going to happen in this? These guys cancel, right? They would both, and now the moles are all on the other side. Except we're ignoring the other side because the other side is neutral. So what's my pH now on this one? Only on this page. It's going to be different on the next page. If it's a neutral pH, the pH.
7.
Yeah, pH is 7. That is only, that's key, only if it's a strong acid plus a strong base. And it's way back to the question I asked, why we can ignore the sodium chloride, because it is neutral. On the next page, we're going to see what we make is not neutral. All right, so what the curve looks like. This is, in this case, it's at 50 milliliters. We'll go through how to find the volume on a next page or the page after. You are suddenly at a pH of 7. And it is a cliff. You cannot mountain bike up the equivalence point. You need a rope and a Sherpa, which you all have a Sherpa as a teacher. You don't want me. There's a Yeti behind me in the picture. Can't see him. Tom and Jerry are there. We're all pulling you up. It's a cliff. So there I am. You guys can all come up here with me. It's my new hairdo. All right. And there you are, climbing the cliff. Okay, I'm getting up there. All right, it's a cliff. It's straight up and down. One drop. You guys who did titration, try to remember back and that one drop. And that's actually why I'm dressed like I am today. And hold on. Actually, bought this outfit for today, and then we don't have school. But you're going for a perfect pink, and that is the equivalence point. And then you guys all remember, if you did a titration, you add one drop too much, and you get this color. It suddenly goes to this color, because this is one drop, that's the second drop. You're suddenly up there with me. And that pH is like 11 pH. Because what happens with that one drop more is suddenly you have one drop more of this, and you have more base than acid. So suddenly the pH is basic. All right, so that's a pH curve of a strong acid plus a strong base. We're going to come back and compare to that. We'll see how it goes today, how far we get. The question at the bottom, hold on, I want to see if I want to do it. I think I want to do it on the next page. I can turn my pages. Yeah. So question 6, is that what it is on yours? Or 5? Question 5, when you add 60 mils of NaOH, that's excess. And so now you're up at the top of the cliff. So now you're at the top of cliff. Congratulations. It's not really congratulations, it means you screwed up. Yeah, do the titration over. But, all right, I'm gonna move on to the next page, because the next page, the next 2 pages is what we're really gonna be doing. This was with a strong and a strong, and we'll see some questions with that at some point. All right. I am going to erase the board. You guys lost the eraser. And you can take a look at the next page. You can do the first question if you want. All right. Got it, Tom? Very good. All right, the difference on the next page is it's no longer strong, it's weak. That's a very weak pen to show you an example of weak. And I think I do acetic acid. So we're gonna do 50 milliliters, 0.1 molar acetic acid. So it has a Ka value. So it's not that our math actually became harder, it's just we have the Ka stuff. And this is why we did all the practice with acids and bases, so now we can do this more involved math. All right, so step 1 is initial. Do it over here. Again, initial means before you add the NaOH, It's an x squared problem. This is back to a question a couple of you were asking in my office hours. Buffers are never an x squared because you always have the acid and its conjugate base. Here, initial, only the weak acid is present. If there is only one thing present, it's x squared, and then it does matter, you have to use Ka. If only a base is present, which is going to happen in a couple minutes, it's x squared, and you have to use Kb. All right, you guys know how to do it. You solve for x. X is your hydronium, and you'll get my pH. I'm not going to go through those steps, but I am willing to, after the lecture, if somebody has a question, or during office hours, and all my blue pens. All right, bonus question time. If you go back a page, our initial pH was 1. Why is this pH initially 2.87? Why is this pH higher? And again, give a couple moments.
Oxygen.
What?
Oh wait, no, never mind. No, it's not right.
It's because we have a weak acid, right? It doesn't disassociate completely.
Yes, that was the answer I was looking for. So Harrison got 2 points today. So those of you who already answered, kind of just count to 5 or 10 before you answer. So if nobody else answers, you can go for it again like he did. You have to count to 5. Harrison, you now have to count to 10 because you have 2 points. It's a weak acid. It only partially dissociates. So the pH, the initial pH is a little bit higher. And we will, when we get to the end of this page, we'll draw the 2 titration curves. The lab that you're going to have for Monday is all calculations for titration. You have one like whole page on your study set, and then you're going to get to do more, and you're going to be comparing and answering questions just like Harrison did to explain why. All right, now we're going to add the strong base. And so this is like what we did with buffers. As soon as you're adding a strong, we have to write an equation. A little bit easier in buffers because all we have is the CH3 CO2H plus the NaOH. All right. Tom, I need your help. One arrow. This hydrogen and the sodium switch places. So we get, it doesn't matter if you show the sodium first or last. So CH3, CO2 has a negative and then the sodium's there. Or you can write it as NaCH3, CO2. They're the same thing. They're the 2 accepted ways of showing it. The H is now with the H2O. This is a question actually 3 or 4 of you asked me during office hours today. You ignore the H2O. You don't have to write ignore. You can write it in your notes because it's H2O. I'm showing it because it allows us to have a balanced equation, but we're going to ignore it because the next step is Tom and Jerry's favorite step, which is the mice chart. All right, first thing we do, we take this information, volume times molarity. Whoops. That number we keep using. This whole page, this column, our initial for the CH3CO2H is always going to be this. Wow, my pens are not doing well today. All right. So the sodium hydroxide is going to be the column that keeps changing. I've added 20 mils, so 0.02 liters times my 0.1 molar. So this is 0.002 moles. So it's just the volume times the molarity. Please show units. All right. This is a bonus point again for somebody who hasn't gotten one. What's my initial on the other side? It's really easy. Starts with a Z and ends with an ERO. In titration, your products start at 0. And as we're titrating, that keeps changing. All right. We're going to subtract limiting reactant. Subtract. So my NaOH is canceled out, and on this side, I add. All right, another bonus question, or something for those of you playing along at home to consider. I'm not going to ignore that number this time. We need, so this is now, wow. Here we go, I found a good pen. I have 0.003 moles, and I do want that number on that side. I need both these numbers. Why do I not ignore that number this time? You're muted, Harrison. I don't know if you're talking to me. Because this is the conjugate base of a weak. It definitely influences pH. So it's only when you have sodium chloride that you can ignore it. This time, you can't ignore the sodium, but this piece definitely affects pH. All right, this is my weak acid, 0.003, and this is the conjugate base. Your Ka formula, you guys know it. Take a moment, write down your Ka formula, which is conjugate base hydronium over the acid. You can either say A, you can say Wa, you can say acid. This is not an X squared. We have the conjugate base, we have the acid. The only unknown is the hydronium. As soon as you start mixing, it's not an X squared. So you solve for X, and then you go to pH. And I'm not going to show every single step because you guys have the idea. I do have a question. See if you remember this or if you understand why from yesterday. You can set it up like this. The Ka was what, 1.8 e to negative 5. My question for you is, earlier I asked, and Jessica correctly answered and said, you have to be molarity. But I'm leaving this in moles. So why am I okay to leave it in moles? Does anybody see or remember why? I talked about it yesterday, and a quick comment for you is if you're ever unsure, always go to molarity when you plug in.
The ratios are the same?
It has to do with you're going to divide by the same volume. So Aaron got it, yes. So the volume would be our total volume. And so we would be dividing by 0.07 liters for both of them. So it's an extra step. So if you have both the conjugate base and the weak acid, you can ignore the volume. But if you're ever unsure, just put it in there and do the step and go to molarity. You get the same X. You can actually do that, try that, and prove to yourself if you're unsure. All right, our pH went up. So this is step 2, our pH is 4.57. And it makes sense. We added a strong base. So we've increased the pH from where we started. All right. Now this, I'll ask it, maybe somebody sees. The pH is going up much faster than on the previous page. So on the previous page, we started at 1, and before we hit that cliff, that straight up and down, all it got to was 2. We keep adding and adding and adding, and here we started higher, and we've almost gone up 2 whole points. Why are we changing faster?
Is it because it's a strong base?
It's a strong base, and you're half there, Juliana. Because it was a strong base on the other side. What is it that we're adding the strong base to that is different this time?
It's a weak acid.
The weak acid, the strong base is like takes preference. And the full answer would be, so in case I ask this again, the conjugate base affects the pH. So the conjugate base, I'm going to give it to her because she wore bunny ears yesterday. And so if you're going to dress up like your favorite Tom and Jerry, like if you want to dress up like Tom and Jerry, great. So the conjugate base is affecting the pH. On the previous page, we ignored the conjugate because it was sodium chloride and it doesn't affect pH. But now we're not ignoring that. So not only are we adding a strong base, but we're getting a conjugate base and that affects our pH. So we're going to see when we make our pH curve, and actually, why don't I do that? I'm gonna erase some. Tom, you're gonna erase a little bit up here. We'll do it up here. The volume, we're starting higher because it's a weak acid, so you're going to start higher and you're going to actually go uphill before you hit this cliff. So this is initial. I'll just put an I. Here we have a weak acid plus a conjugate base. So my pH has a slope. On the previous page, the conjugate base, there was no conjugate base. It was sodium chloride. And then this is special. This is our equivalence. And then up here, this is excess of, I'll just say SB for strong base of the sodium hydroxide. And we'll see this curve as we're going through it, and it shows up in your homework and stuff, and we can talk about it more. But it is slowly changing. All right, let's do those next 3 points on here. And so this is kind of a guideline. You're going to be asked, like, where are you in the titration? So you're either here initial, you're here, this is called pre-equivalence. So the only point that really matters in the titration is that equivalence point. So right now we're pre-equivalence, and here you can either say I'm at the excess point, or you can say I'm post-equivalence. really the two answers. You're after the equivalence point, which means you have excess of the strong, and we'll do the calculations in a moment. We're going to do the half equivalence. And let me get rid of this part. Too much. All right. So before I do the half equivalence, let's skip down and talk about the equivalence for a moment. The equivalence point means something is equal. So, and somebody who doesn't have a point yet, if you want to try, what is equal at the equivalence? So I've skipped down to number, oh wow, it's number 8 on your thing. At the equivalence point, what is equal? Anybody? You can go back and look. It is
The acids and bases,
almost. What about them?
them being strong.
No, what about them is equal?
Oh, their pH.
You almost had it. They're moles.
Oh,
It's chemistry. You should know that. That's what chemists talk about. Everything about chemistry is moles. In fact, when you guys take physics and you do gas laws, they kind of ignore the moles a lot. They do everything with grams, and they have, and like in chemistry, we did a lot with moles. So it is the moles of your reactants. So in this case, like in the previous one, and I know that's why you said it that way, it was the moles of your strong equal the moles of the strong. In this one, it is the moles of the weak acid would equal the moles of your strong base. So we're going to do that calculation in a minute. I'm going to back up, though, and we're going to do what's called the half equivalence. This question that I asked, you're going to be asked it again and again and again, because that is what titration is about. It is one of the most important assays, quantitative analysis techniques that chemists do. And so I'm very sad that you guys are not allowed to do it this summer, because it actually helps to do this, but we'll be okay. You can always watch a video, I suppose. The half equivalence is when you're halfway there, not in pH, but it means that half of this is gone. So it would mean half of it's reacted. So where did that half go? It went to the other side. So at the half equivalence point, your weak acid equals your conjugate base. And again, I have a reputation. Some of you, your other teachers would have said, oh, you better show moles, because Sherp is really anal about that. It's because it's important, because if you're not in moles, none of this works. The moles of the weak acid equal the moles of the conjugate base at the half equivalence point. At the equivalence point, it's the two things that you're reacting. So the weak acid and the strong base in this problem. All right, so let's finish the half equivalence point. So write down your Ka expression. I'll write it over here. So this is why this point is really important. If the conjugate base and the weak acid are the same, they cross out, they're no longer there. So at the half equivalence point, you're going to race with your buttocks. All right. So only at the half equivalence point Ka equals the hydronium. And if we take a negative log of each one of them, the pKa equals the pH. It means we don't need to do a mice chart. That is why I should have given you more here because you're writing notes, but you're not going to ever get much space for the half equivalence because this is all it is. That's a P. The pKa equals the pH. They are the same. So you guys can just do the negative log of our Ka, and you'll get the 4.74. So we are here. This is our half equivalence. So our pH is increasing slowly. You're going to also label the volume. And we're going to know the volume when we do the equivalence point. And a reminder again, for this page, I did easy numbers. So I made the molarities the same. If this is 0.1 molar and this is 0.1 molar, at the equivalence point, then they're both going to be 0.05 liters. Because everything's equal then at the equivalence. That's not going to hold true when we get in a couple of pages. So I'm going to finish my graph. If my equivalence is 50 milliliters, and again, you're going to have problems, and when we get to the fourth page, where we're going to have to figure out the volume. Then my half equivalence is half of whatever that is. So if that's 50, that's 25. And all right, that's the idea of half equivalence. And this is why your homework set, actually your homework set's 4 pages, but that's because the very last page you're going to draw a titration curve. So I gave you a whole page to doodle it. And that's why you're going to have a lab then due Monday that just has you doing more of this. All right, we're going to do the equivalence, unless there's a question on the half equivalence. Right. So equivalence, these guys are equal. This is 0.005. This is 0.005. What's the limiting reactant? They both are. They are perfection. It's that moment, if you do any kind of balance pose, we have that moment where there's no fluctuation. They cancel each other out. It's completely reacted. This is back to the stoichiometry we did back in 221. One-way reactions. This is going to be an x squared problem. So at equivalence, these are equal, only the conjugate remains. That determines your pH. On the previous page, the conjugate was sodium chloride. Sodium chloride has no impact on pH, so we're neutral, pH of 7. This is a conjugate base. We could cross out the sodium. So it is the question every year on the first midterm where I have you cross out and tell me if it's an acid, a base, or neutral. And it is the most missed question every year. It's our really important question. You cross out 1A's, which is going to be sodium here, and we're left with a conjugate base. We can no longer use Ka. So Jessica, this is back to the question you had asked me earlier in office hours. If you have the acid and the conjugate, as long as the acid's there, you can use Ka. But the acid isn't there anymore. You only have a base. You have to switch. So at the equivalence, this is another thing, you have to switch K values. Wow. I'm putting a vice versa because if you started with KB, now you switch to KA. If you start with KA, you're going to switch to KB. Really important pieces there. So it's because of this word only. How do you change KA to KB? 10 to negative 14 divided by the KA. That's because Ka times Kb equals 10 to negative 14. It's a lot easier to write it like this. Write your formula, hydroxide, conjugate acid, over the weak base. This is my weak base. So suddenly the reaction changes. This chart, our mice chart, is just to get us numbers so we can plug in to the second equilibrium that's happening. So the mice chart makes the weak base, and now this weak base dissociates and has its influence on pH. This is x squared. Your X is your hydroxide. So you negative log, you get to POH, then pH. You guys know how to do that? Or you need to come and talk to me during office hours and just say, hey, can we go over this specific problem? So if you come to office hours and you have the problem you want to go over in front of you, I can pull it out and we can talk about it. So this is my question for you all. You're going to get the wrong answer with what I have up there. What am I missing? And why does it matter now? Anybody can answer.
It's non-molarity, right?
You have to be in molarity. So yeah. You have to have the total volume there. So you have to figure out the volume of the NaOH. The way you figure out the volume of the NaOH, I'm going to show you here. You knew the moles had to be the same as the other one. You know the molarity is 0.1 molar. That was given. If you flip the molarity on its head, so if you take moles divided by molarity, you get volume, and that will be 0.05 liters. We add our two volumes up, so 100 milliliters or 0.1. And so, yeah, Aaron, I think that was you who said that you have to have molarity. So if you want the point, Aaron, you're going to have to tell me why it has to be molarity suddenly.
Oh, because X has to be molarity, right? Oh, wait, because I'm trying to think, the two X's have to equal each other in molarity. Oh.
Primary track. You don't have a ratio on this problem. So if you guys go back to the previous one, we knew two pieces. We knew the weak acid and the conjugate base. Here, it's x squared. Whenever it's x squared, you have to be in molarity. Whenever you plug into pH, you have to be in molarity. if you're doing where you know a weak acid and it's conjugate base and you have both pieces, you can have them both in moles or both in molarity, because there the volumes will cancel. Here we have nothing in the numerator to cancel the volume. So yeah, you punch in and you get my pH 8.72. So I'll write it up here, 8.72. It's on your answer key. That's our pH. So here's the question, and this is a really important question. Why is the pH not 7? If it's equal, doesn't equal mean a pH of 7? Why is it not neutral? Anybody can answer.
Strong base, weak acid.
Keep going. He's right, strong base because we have a weak, but why does that matter?
Uh-oh. Well, I mean, strong base is more basic. That's the best I got.
Anybody else? Aaron, I'm going to give you half a point for that and half a point for the one before. So it is what Aaron was saying, what I was looking for from him, because our conjugate affects the pH. And we made a conjugate base. On the previous one, we made sodium chloride, which has no effect on the pH. So the conjugate determines the pH, and it's a base. So the pH is above 7. It was a question on your midterm number 1. When you did it was the sodium salt pH one, and then it said, does your answer make sense? And so far, half of you have gotten it, which is like breaking the record of all time, because usually nobody gets that one. It makes sense because it's a conjugate base. The pH should be above 7. Right, we're gonna do one more on this page, and we'll move on. Go ahead.
So are you saying, so it's because the WA and the weak acid and strong base cancel each other out, so then the conjugate base is the only one there? Is that?
Yes.
Okay, cool.
Your answer was correct. I was wanting you to go to what you just did. So yes, the strong base is stronger. Why does the strong base have more impact? And it's because even though these guys neutralize each other, they made a conjugate, the weak acid became a conjugate base, and it affects pH. All right, to do the last problem on the page, I'm gonna erase. Tom is so excited to erase. Jerry is having troubles today. All right. We're now adding 60 mils of the NaOH. So you have 0.006 moles. This was a question somebody asked me earlier, and I apologize, I can't remember now who it was. I think somebody asked me this yesterday during some time, I don't know what. Your limiting reactant is no longer the strong acid or strong base. So the question several of you had asked me was if the NaOH and HCl is always the limiting reactant. I think it was you, Jessica, during office hours. And I said, if it is a buffer problem, yes, or else you made a mistake. If it's a titration problem, it means you're post-equivalence. And so we have excess NaOH. So and this is the last problem on that page. So excess NaOH, we're post-equivalence. So we're going to finish our chart because that's actually important. Our limiting reactant is now the weak. Our weak acid is gone. The other big thing to get from this page, and we're going to do one more page, is that weak acid number just kept being the same. It doesn't change. It's the NaOH that changes. And whichever one is smaller is your limiting. And we do add it to the other side. So it's our X value. It's just we know it for these charts. Now the key here is we don't have to mess with KAs or KBs after the equivalence point, because this is excess, this is a strong base. You can plug right into negative log of hydroxide. That will give you your POH. However, you cannot plug in 0.001. Why? You're gonna get the wrong number if you log that number.
That's mole, not molarity.
Yeah, if you don't have the two pieces in that ratio, in the Ka or Kb ratio, you have to be in molarity. If you're ever in doubt, go to molarity. The volume is the total volume. So we had 50 mils, the original 50 mils, and now we added 60. So for the NaOH, you're stopping at each point. Don't add all the volumes up. So this number will be the negative log, I have no idea, 0.001 moles over 0.11 liters. And you would do that. That's not going to be your pH, that's going to be your POH. And you guys know how to change it. And we actually get a pretty high pH, so closer to 12. So up here, we're around 12 because we have the excess. All right. We're going to move to one more page. Let's see if we got it. Questions. I'm going to erase unless there's a question. Tom, you lost the eraser. You hid it somewhere. All right, Tom just wants to erase. He's like, you guys can look at the next page and see where we're at. We are going to do a weak base plus a strong acid, HCl. So as I promised yesterday, when there's a strong, the acid will be HCl. If it's a strong base, it will be NaOH. Once you see those, you're going to write a reaction or the equation out. All right, so step X is initial pH. So it means all we have is the 50 mils of the 0.1 molar NH3. This is a base. So if nothing else, you guys see nitrogens, you're thinking base, right? Hopefully that got ingrained in. Nitrogen is base. We need a Kb. Oh, I gave you Kb. It's an x squared y. Well, I told you, there's only one thing present. There's only NH3. So it's an x squared. Just be careful, it's Kb. X is going to be your hydroxide. You guys know how to solve these. We're going to move on. So now we're up to Xi. All right. And we're going to add HCl. So NH3 plus HCl. And go ahead and finish your equation. This one is interesting. The hydrogen, of course, moves over here and we get NH4. And then the Cl is attracted to it. You don't have to show the plus and minus. I like to, it's a teaching tool, because you get ammonium and chloride. Aaron, this is that question you asked me. This is ammonia, ending with IA. This is ammonium, because it has 4 bonds around it. This question you asked me a couple of days ago. All right, we're adding NH3, so we're going to do a mice chart. So we take our volume times our molarity to find moles. So once again, a quick disclaimer, these 3 pages, I picked really easy numbers so I could get through the big picture of the lesson. The HCl is 0.02 or 20 milliliters times 0.1 molar. All right, here we go. What's my initial on the product side?
0.
It is 0. Thank you. A reminder, buffers, first page of your study set, your worksheet is about buffers. There is never a 0 in buffers. Titrations, you have a 0. So if you've done your buffer stuff, get that first page of the study set, do your worksheet, say I got buffers, and then finish your study set. It is due by midnight Friday night before we turn into pumpkins for the weekend. All right, limiting reactant, we subtract. You can write the 0. I like to cross it out. I don't know why. All right, this is a question, Jessica, you asked me during office hours. NH3, not this question specifically, is a base. This is the conjugate acid. You can absolutely use KB. You guys don't have to write all this down. I just need to, well, you should. But when you do your homework, make it pretty. I just looked to see if you did it. The homework is meant for you to practice for the real thing. I had a student one year and his homework was always a mess. And he just said to me, oh, I'm gonna make it real pretty for you, don't worry. So, but practice, the whole purpose of the homework is to give you practice so you become really good at this. So next week you're ready to move on and you've got this. You've got this down. It was a question Aaron asked me today. He said, is this the hump? Titrations is, because it's all these steps. You get through this, it can be much clearer sailing. So put the time in, get this, feel good with it. This is why your lab for Monday, you'll get to do more with this. All right. We have the conjugate acid and we have the base. You can plug into KB. If you use KB, your only X is hydroxide. Your X will be hydroxide. I personally just solve it with KB because I already have my KB. However, you can switch to Ka. Oh, I know what her question was. She was on the second page of the worksheet. And I gave a KB on the worksheet. You can now, because you do have both of these. Again, it's a matter of which are you calling the conjugate. So you would call that the acid, this the conjugate base. So it's kind of up to you. And you would solve, in this case, X is your hydronium. So if you have both of them, it doesn't matter. And that is a buffer problem. When you're here, you can use Ka or Kb. Initially, it matters, and at equivalence, it matters. So that initial pH and at equivalence, X squared, it matters. The other places, it doesn't. That means that also you can leave it as moles, because again, it's a ratio. The volume doesn't matter. All right, you'd punch it in, you get my pH. I'm assuming I gave you pHs. We're going to move on. I'm going to erase just part of this. Tom can erase part of it. All right. So I'm always asked a question when people are doing the homework. And they're like, do I have to keep writing the equation for every problem? You know, you guys, again, your homework set is meant to give you the practice so you have it down. So yeah, I would get in the habit so you have it. So we're going to do the half equivalence. Half equivalence. Moles of the NH3 are going to equal the moles of its conjugate acid. These guys are equal. So these will cancel out, or these will cancel out. So this is the point at the half equivalence where the Ka equals the hydronium. Or you can say the pKa equals the pH. What if you were talking in terms of Kb? So again, count to 5, give somebody a chance who hasn't gotten a bonus point. What's the Kb equal to at the half equivalence? Well, these two cancel. So Ka is going to be the hydronium. If you're solving with Kb, Kb will be your hydroxide. So if you know the hydroxide, you guys know how to change to hydronium. That's the half equivalence. All right. My answer's there. You can play with it. Several people have asked me how they can do better on the next test. You got to go back and redo the notes and do all these steps that I'm leaving out. That's my recommendation. Go back and do the notes so you feel really comfortable with this. Go back and redo study sets. All right, at the equivalence, the moles of your reactants are equal. So in this case, my NH3 and my HCl will both be 0.005. So again, only the conjugate. Remains. So this completely, these guys canceled. So can we use Ka or Kb, or does it not matter? And explain why. So this is the last bonus, or actually there'll be one more. Anybody? Any thoughts? Does it matter? We use either one? If you only have one thing present, it does matter. So this is where you have to ask yourself, this was that piece from the last exam that was a lot of you struggled with, and then you got it as you did practice. And so this is an acid. So you have to use Ka. So at equivalence, we had to make the switch from Kb to Ka, because we no longer, the base is gone. All you have now is the acid, the salt, the conjugate. It is also an x squared problem. So you have to divide by the total volume so that you have molarity. And it's just like initial. Initial and equivalence are x squared. You've heard me talking enough, so I'm not gonna like go through all the math. I recommend you try it. The answers are there. And then you can say, come during an office hour and say, hey, can we walk through this page in the notes? I wasn't getting your answer. I do want to go through the very last problem, and I want to draw a curve, and then we'll be done. And the last problem on the page we are past the equivalence. Oh. Now we're going to be post-equivalence. We have excess HCl. You still do an ice chart. You want to figure out how much excess you have. And I know online these people have these elegant tricks. Oh, you're going to be labeling so much to be able to clearly show. These mice charts are wonderful. The text that I posted, this is probably chapter 18 in that text because it's always been that chapter. You can look through that, and they do these mice charts. And I remember Bernadette came back, she was my student, and she was like, oh my gosh, those mice charts were like a saving grace when I went on in chemistry at Portland State. All right, this is excess of the HCl. It is a strong. So you can do negative log of the HCl. After the equivalence point, you don't have to do Ka or Kb. However, you have to use molarity. So you have to divide the total volume, so 0.11 liters. Moles over volume, plug it into there. And the pH, it makes sense. Like I'll ask you at random points, does this make sense? And so for that last step, absolutely. We have excess of a strong acid, our pH should be really low, and it is. All right, I want to draw a titration curve, but before I erase to make room, I'm really missing having 9 boards around the room where I can just keep writing, and you guys can just keep turning your chairs. Is there questions? I'm going to erase and draw our curve. And again, if you have the notes, you have them pulled up, my answers should be on your guys. So this one is going to look different from the previous ones. Last bonus question. Why is this one going to look different? What is different about this page from the previous 2 pages?
Is it going to be opposite where it starts high and goes low?
Thank you,
Because
Margaret. She's got it. Yes, because we're starting with the base. So we're going to start high. If you're starting with the base and you're adding the acid, and we're going to end low. All right, we have to connect it. So it is weak. So we're going to actually see this downhill and then the cliff. That's a cliff. If you are mountain biking, if you're kayaking, this is like you just went over a waterfall. It's not a gentle waterfall. This is like the gentle meandering stream. And this is like Multnomah Falls. Are we allowed to go to Multnomah Falls yet? All right. So up here, what was my initial was 11.13. This is only the weak base. In here, in that area, we have the weak base plus the conjugate acid. And then this is our most important point, pH. This is our equivalence point. This was 5.28. And in the notes, this was 50 milliliters on this page. You can also do the half equivalence, which would be half the volume, not half the pH. It is half the volume. So that would be, your curves don't have to be perfect, but let's aim for it. So 9.26 pH. I guess I can do it over here. And then my final, we figured out, is 2. This is excess HCl. You don't have to get to 60 to get to excess. You're at 50.01 milliliters. You've hit excess. This is a cliff. And again, if you were biking, you're going to fall. Oh no, that wouldn't be good. You can have fun. You can draw people rappelling down. They can be on a rope. They can be hanging upside down. But they're going to be safe. And they can be rappelling. And they can have like an astronaut helmet on.
I have a question.
Go ahead.
Is this pretty much what you want on the last page of the study set? Just
The last
this?
page of the study set, you're going to be drawing a picture of whatever the titration is. And then also the lab that I have to finish writing because I have to create all new labs for you guys. So it'll be up by tomorrow, if not tonight. You're going to be drawing a couple titration curves and labeling them. Does that answer your question? I think that was you, Margaret.
Yeah, thank you.
All right. Questions? I think the one on the study set was a weak acid plus a strong base, so it's going to go uphill. My question for you is, I'm figuring you guys have enough, but if you want, we can do the last page. I was actually willing to do a lecture tomorrow, or I can tape it myself. It will take about a half hour to do the page, but I'm figuring everybody needs to take a break right now, including your teacher. And then you can let me know. I'm going to stop recording.